Mole-to-mole stoichiometry is using mole ratios to get from moles of a given chemical to moles of the desired chemical. So as in any stoichiometry problem, we are always going to use the mole ratio. So the very first step is we have to make sure we have a balanced chemical equation, because a mole ratio comes from the balanced chemical equation. So if you will take a minute to inspect this chemical equation, you'll see that it is balanced. So you can pause this for a minute just to check to make sure. Okay, good. Now let's take a look at the problem. Given 4.5 moles of pentane, C5H12, how many moles of oxygen are required to react with it? So we know this is a stoichiometry problem because I'm given an amount of one chemical, pentane, and I'm trying to find out an amount of a different chemical, oxygen. And these two chemicals are related by a balanced chemical equation. So in any stoichiometry problem, we want to be really clear about what chemical we are given an amount of to start with. And in that case, it's going to be pentane. We're given 4.5 moles. And what chemical we're trying to find an amount of. And in that case, it's oxygen. And the reason we want to focus on that is because these are the two chemicals that are going to be in our mole ratio. And we want to remember that our mole ratio always has the desired chemical, the chemical whose amount we're solving for, in the numerator, and the given chemical, the chemical that we're starting with, the amount that we already have, always is in the denominator. And that will always, always, always be our conversion factor. And the mole ratio will also have these stoichiometric coefficients from the balanced chemical equation. So as we set up to solve, I have a very systematic way of setting everything up, and it never fails me in terms of getting the right answer. Clearly identify the amount and the chemical that we're given. In this case, 4.5 moles of C5H12. Clearly identify what we're trying to solve for, moles of O2. And then write down our conversion factors. So in mole-to-mole stoichiometry, where we're given an amount in moles and we're trying to solve for an amount in moles, our only conversion factor is the mole ratio. And that's super easy. It just comes from the chemical equation, where our given chemical is in the denominator, stoichiometric coefficient from the balanced chemical equation, and the desired chemical is in the numerator, stoichiometric coefficient from the balanced chemical equation. So if we do a double unit check, which means we check to make sure we have two of every unit, looking at what we're given, what we want, and our conversion factors. If I have two of every unit, I'm ready to do my railroad math. So moles of C5H12, moles of C5H12, two of those. Moles of O2, moles of O2, two of those, I'm ready to start. With our railroad math, we always begin with our given chemical. So 4.5 moles of C5H12, and I've already set up my mole ratio the correct way for the given chemical to cancel out, with moles of C5H12 in my denominator. So moles of C5H12 divided by moles of C5H12 cancel out, and the units I end up with are moles of O2. Looking at the numerical value, 4.5 multiplied by 8 divided by 1 is 36. So remember, in chemistry, you have two values to consider when you're solving any math problem. You have to do the numerical part of it, which your calculator will help you with, and then you have to make sure you have the right unit. And if you set up your railroad math correctly, your right unit will always result. So this makes sense. If I look at my balanced chemical equation, 1 mole of C5H12 requires 8 moles of oxygen. So if I'm starting with 4.5 moles of C5H12, it makes sense that I would get 36 moles of O2. If I had 4 moles of C5H12, 4 times 8 is 32. And if I had 5 moles, 5 times 8 would be 40, and 36 is right in the middle between 32 and 40. So this answer makes sense. So it really is that easy. In mole-to-mole stoichiometry, you take moles of your given, multiply by the correct mole ratio, and you'll end up with moles of the desired chemical. So I want you to try it right now. Look at this problem. If 6.36 moles of water are formed from the combustion of pentane, how many moles of carbon dioxide form? So pause this video, solve, and when you get an answer, start the video again and we'll review it. So here's the problem as I set it up. Balanced chemical equation, the top, what I'm given clearly identified, where I'm trying to get to clearly identified, and this helps me set up my mole ratio. My given chemical is in my denominator, moles of H2O. The chemical that I'm solving for, moles of CO2, goes in my numerator. And these numerical values are the stoichiometric coefficients from the balanced chemical equation. So moles of H2O would be 6, and moles of CO2 would be 5. So that's my mole ratio, my conversion factor. That's going to get me from moles of water to moles of CO2. So in my railroad math, I begin with what I'm given, 6.36 moles of H2O. I multiply by my mole ratio. My moles of water cancel out. 6.36 multiplied by 5 divided by 6 gives me 5.3. And I've expressed my answer with 3 sig figs because I was given 3 sig figs. And my units are moles of CO2. Those units didn't cancel out. So if you got this, give yourself a pat on the back. And after you get a firm handle on mole-to-mole stoichiometry, you're ready to move on to mass stoichiometry.